May as well turn them on anyways. You can skip forward in the video if you don't want this stuff. Okay, so I want to go over homework that we did for problems for section 10, and then homework for section 12. Those were the two focusing on sets. And A, we need to make sure that you understand what exactly this symbol means and this symbol means. And then B, you need to know how to do a proof with a set. Another hint when you're doing a proof, if you're not using a definition, chances are you're doing the proof wrong. That's why definitions are given to you. I mean, you have a definition of what an even number is. You have a definition of what a subset is. You have a definition of what it means for two subsets to be equal. We have an exact definition of what exactly we mean, and your job is to precisely show, using that definition, it's true. It's very precise language. If you're ever thinking, well, it's just obvious, is it? That's a tough thing to say. You need to precisely go through it line by line exactly why what you're saying works. So let's go over each of these, and do you have access to your books? Because it'd be good if you could see the problem. I guess you have your homework, so you can probably know what the problem is and what you did wrong.
So we're starting on section 10.
So I'm going to go through section 10 homework and then section 12 homework. Make sure that it's just as clear as can be what exactly we need to do. Oh, one more piece of bookkeeping. How many do you guys saw your test from last week?
Yeah. Yeah, what happened?
Yeah, so the grades got corrupted.
Okay.
I don't know what happened when they were like saying, where do you have your test from last week?
I'm not sure. Not here.
Do you remember what the score was by chance?
No.
See if you can find it and get it for me. See if you guys can find and get it for me so I can enter your grades.
What am I?
Yeah, I just need your grades again because I don't know what happened there. Like something got weird. I think I must have like been editing and like closed it and saved something that I didn't mean to save.
Our chapter 2 test?
On your chapter 2 test, yeah. Let me log in real quick so I can just enter them and make sure that they get in good and then move forward. Yeah, sorry about that. I have no clue how that happened. So, oh, I didn't put in all your guys' chapter 5 homework either. What the heck is wrong with me?
Chapter 5.
Or,
Chapter 2.
homework 5. So homework 5, I need to take your homework 5 back real quick. I'm putting the scores.
Okay.
Sorry about that.
Okay.
Jeez. And
I'm
then,
going to just tell you my score.
1 second. This stupid thing trying to be smart. Just showing you for some reason I have your homework 5, but I don't have theirs. That's weird.
Alright. My test was
1 sec. One at a time.
okay.
So I gotta actually do a calculation of what to enter because it was worth 20 points. What the heck? See, yeah, I remember that. I entered that. It was just Sony's was graded first, so hers got saved and the other two didn't. I already got yours. You have your homework 5?
Yeah.
Okay. Let's get all your guys' stuff up to date. Okay, and then you said you had your test?
Yeah. 37.
Out of 40. Okay. Have your test.
Wait.
Oh, is that the wrong one? Is that a 9?
It's gotta be, right?
You have your test too?
I know.
You don't?
No.
Do you think you threw it away?
It's possible. I don't think so, but it's possible.
Do you at all remember what your grade was? Or even as a percent?
I don't remember what it you got.
It was in the 20s, like 24. I'm not exactly sure, that's why.
Well, we'll take your best guess until you give me something different. Because I don't know what else to do.
That's good with me.
Because I have no memory of it. So yeah, sorry about that. That sucks. So I should probably just like hang on to your guys' stuff for a week just in case.
I'm happy to hang on to it. I do that anyway. So.
Yeah, I
I have all
That's
my
good.
stuff so far.
Okay, so I got all your guys' stuff in. Should be up to date. And again, it's possible that some weird thing could get corrupted, so make sure you look at those online. If something's just like way
Yeah, I was
off,
wondering,
let me
I
know.
checked online and I didn't see it. Figured you would have been in
Yeah,
there, so I was
I didn't
confused.
see it, so
Yeah, I don't know what happened. So sorry about that. Okay, so now section 10 homework. Section 10, 10.1a. So we want the set of all natural numbers less than 10 that are divisible by 3. 0, 3, 6, 9. Easy peasy. Number 2 is a set of all integers where x is prime and divisible by 2. 2 is the only prime number divisible by 2. Good?
Hey, hang on, what? Oh, right there.
10.1, just a B. C, the set of all integers such that their square equals 4. 2 squared equals 4, negative 2 squared equals 4. D, the set of all integers such that their square equals 5. There isn't one. There's no integer that if you square it you get 5. So that set is the empty set. That's the set of all integers whose square is 5. E, the power set of the empty set. What is the set of all possible subsets of the empty set? The set of all possible subsets is just the empty set. Good? F, the set of all integers that are divisible by 10 and that divide 100.
Oh, remember doing this, Curtis?
Yeah.
That was so dumb with me.
And the weird thing is, I understand you guys forgot the negatives, but no one even thought of 100,
Yeah, like,
which was really weird to me.
I should have got that.
Oh, did you all work on it together?
No.
No.
But you all got the exact same thing, 10, 20, 50. See, I thought that was really strange. And then G, I thought you guys had a hard time with, maybe I'm misremembering. But G is the set. Sorry, I lost my place. G is the set of all subsets of the set 1, 2, 3, 4, 5, whose size is 1. It's the set. I missed my closing.
Oh, yeah, I think we read that wrong.
Yeah.
It's the size.
So make sure you understand it. It's the set of all subsets. Oh, that's why you guys put 1.
Yeah.
The absolute value of 1 equals 1.
Yeah, that's what I was thinking.
I could not figure out what you guys were thinking on that one. Okay, so that now makes sense. You're thinking of absolute value.
Yeah.
Okay. 10.2a. For each of the following sets, find a way to rewrite the set using set builder notation. I think you guys did good on this one for the most part. 10.2 right here. The set of all integers between 1 and 10. The set of all integers between -8 and 8. Divisible by 2. The set of all natural numbers that are odd. And then the set of all squares of natural numbers less than or equal to 10. Right? Take any natural number less than or equal to 10, square it, you get an element of the set. Good?
Yeah.
So on my paper, you wrote instead of the x at the beginning.
Oh, I just made fun of how you wrote x is odd.
No, not x is odd. I'm thinking on this part. So when you say x squared there, x squared such that, is that supposed to be x squared?
Oh, you can write it that way if you want.
Well, that's what I'm wondering.
Well, here's what you said. You said the set of all x, where x is an integer and x squared is less than 100.
Right.
This would give you the numbers 1 through 10.
Right.
You need those squares. The set you're producing is the squares of those.
Oh, okay.
Does that make sense?
Yeah.
So yeah. Now you make me think I should dock you a little more. I thought that was just a miss. Gave you the benefit of the doubt on that one. Alright. 10.3, we're finding the cardinality of sets. So A is the set of all elements whose absolute value is less than or equal to 10. So all the numbers whose are less than or equal to 10 is all numbers from negative 10 to 10. There's 21 of them.
Wait, what? What?
10.3a. There are 21 numbers whose absolute value is less than or equal to 10. Right?
Oh,
Am
yeah.
I saying something weird?
Yeah, that
Okay.
makes sense. Wait,
B.
no?
Okay.
That doesn't make sense.
What's the absolute value of negative 10?
10.
What's the absolute value of negative 9?
9.
So all the way up to 10 again. Negative 10, negative 9, negative 8, negative 7, negative 6, negative 5, negative 4, negative 3, negative 2, negative 1, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Those are all the numbers whose absolute value is less than or equal to 10.
Oh, well, something
Alright? Okay. Next, we were on B of 10.3. The set of all integers whose square is between 1 and 2. That's just negative 1 and 1. So how many are there? There's 2. So the answer is 2. Good? Assume if you're not saying something, that's good. C, the set of all integers in the empty set.
Wait. Couldn't that also be 0
Which one?
on B?
What's 0 squared?
1. No, sorry, that's the It's 0. 0. Oh, wait,
The confidence. Okay. We were on C of 10.3. C. So the set of integers in the empty set. There are 0 integers in the empty set. So that set has size 0.
Okay, I see what I did wrong there.
D. The set of integers that contain the empty set. There are no integers that contain the empty set. If you would have put infinite there, I would have also accepted it.
Infinite?
Yeah.
Yeah, if you would have thought about numbers of sets.
What do you mean?
If you didn't think about it that way, you're fine. Put 0, you're good. Alright.
Okay.
E. The set of all integers that have this empty set as a subset of the set containing that integer. I think you all got this one right. E's infinite. F. I think you understood. So we got the power set of the set 1, 2, 3. And we have this little formula that the size of the power set is 2 to the size of the set you're taking the power set of. Once again, the size of the power set is 2 to the size of the power set to the size of the set you're taking the power set of. So 2 to the 2 to the 3, or 2 to the 8, or 256. I think you guys pretty much got it. G. Let's see. G was, maybe you guys had another word problem with this one. The set of all members of the power set of 1, 2, 3, 4, whose size is 1. The set containing 1 is a set whose size is 1, and it's a member of that power set. The set containing 2 is a member of the power set. The set containing 3, the set containing 4. These are the 4 sets whose size is 1 that are members of that power set. Does that one make sense?
Yeah, I don't know why I got that wrong.
Okay. And then the last one, I don't know how you guys got this one wrong, but you did. H. That thing has a size of 2. There's 2 things in there. There's a set containing 1, 2 in there, and the set containing 1, 2, 3 in
I don't know
there.
how I got
I
that.
don't think
I don't know how you got
I
it.
just forgot to say 2. I was writing out the problem and then I just thought I was done. Just saying.
Um,
I don't know how I got that answer.
so 2. There's 2 things in there.
Right, yeah.
Right? Duh. That's why I was so worried. Great.
Okay, we've already taken a test on this homework.
Yes.
Why wasn't any of this on the test?
Because I can only pick so many problems.
You picked easy.
You're telling me to pick hard problems for my test?
No,
No.
I'm just saying, if this is important, then you would have been testing this on.
I thought that this was clicking in your head better than it was.
Oh, okay.
That was the assumption I made.
I think going on, we got better at it.
So did I. You didn't bother like going back and looking at your homework. That's what I hoped in my heart of hearts.
That what?
That you did understand all this as we continued, but you just didn't bother going back and fixing up your homework before you gave it to me.
Yeah.
Which you really should
Well,
do,
I
because
know
your
that.
guys' homework has
Exactly.
more weight than tests.
I didn't know that it was wrong
So
on my
fix your
homework
homework.
until I got better at it. And then I didn't realize I was wrong.
Well, you read it now and you say, how did I get that?
Yeah, that makes no sense.
So you could have fixed it.
Yeah.
Okay. Continuing, 10.4. Whoa, I got on a different page than that. There we go. 10.4. I think all you guys did this one right. I don't remember. But the thing that baffles me is you did 10.4 is so perfect and it's so bad on 10.5. Because it's the same concept. So 10.4 was just assigning these symbols correctly.
Right.
That's all it was. And I think you all got it right. And there's the correct ones if you missed one. But then this one, I think it's when we get to 10.7 that things go to crap.
So I remember where I saw the 3 dots. I had seen it from a different teacher using it on the work. And I picked it up as a habit.
Second thing to stop doing. Stop using this as such that in a proof.
Why?
Use this.
Oh, I try to only do that when I'm defining a set.
Yeah, only do that when you're defining a set. Because it took me a second to figure out what the heck those 2 dots were. Because I knew that you were randomly using 3 dots for and now it's like 2 dots. I'm like, oh duh, set Miller notation is my thinking. No, just use s dot t dot. That's short enough for such that. Okay, so no questions on 10.4, right?
Yeah.
That one was pretty good. 10.5. So we were supposed to find sets that make each of these statements true. You guys get crazy, making all sorts of headaches for me to grade to crap. Instead of just picking easy stuff. And maybe you're like, maybe if I pick hard enough stuff, you won't really think about it. I don't know. Okay, so we need to find sets that make A a subset of B that makes set B a subset of C. So we need to find sets A, B, and C that make this true. We'll make A equal to B equal to C equal to second containing 1. We're done. The second containing 1 is a subset of the second containing 1 is a subset of the second containing 1. We're done. Let's look at this one. We need A is in B as a subset of C. We'll set A equal to 1, B and C equal to second containing 1. We're done. Continue. We need A as in B as in C. Make A equal to 1, B the second containing 1, C the second containing 1.
So, I have a question on it.
What?
Why isn't the second containing 2 a subset of the power set of 2? The power set of that's fine.
The power set of 2 is the set of all possible subsets. The second containing 2 is in there.
Oh.
It's not a subset of it.
Oh. Okay.
See, and you understood that right here perfectly. And then you use the exact same idea to get down here and you screw up. Which is what was confusing me.
You explained it differently. That's fine.
No,
Well, I don't know about that.
Over there, you explained it differently. You said that, I think it was the brackets, because you said that if it doesn't have brackets on it, then it's not a subset of it. And I think that's where we got confused, because then we thought every time it's a subset of it, then it has to have more brackets.
Well, I must have said something that confused you guys, because you all agreed on this, and the exact same ideas down here went all over the place. So, I don't know what it was, but let's clear it up now. So we got that, let's do this one. A is a subset of B as a member of C. Make A and B the set containing 1, C the set containing the set containing 1. We're done. 10.6. So you're supposed to say when the statement's true, or state that it's never true, and why. So let's go over it. When is the empty set a subset of A?
Always.
Always, but one specific example is when A is equal to the empty set. But we could set A equal to anything and we would have been fine. B, when is the empty set an element of A? Well, we can make A the set containing the empty set. And that's a case where it works. C, when is A a subset of the empty set? In that case, it's only when A is equal to the empty set. But that's still a case where it's true. And then D, A in the empty set, we can never come with a case where that's true. A in the empty set, never, since A in the empty set implies the empty set is not empty. Right?
Okay, C.
If A is equal to the empty set, then the empty set is a subset of the empty set.
Okay.
Remember, a set's always a subset of itself, no matter what it is. So the empty set is a subset of the empty set. Everything in the empty set is in the empty set.
Oh, okay.
Okay. Yeah, just always think back to the exact definition of a subset. Okay, now proofs. Which none of you guys bother to use definitions. Well, you might sometimes. I don't know. A lot of missing definitions, which bothers me a lot. So let's go over it. Proof. If A is a subset of B and B is a subset of C, then A is a subset of C. Okay, so let A, B, and C be set such that A is a subset of B and B is a subset of C. Set up our problem. How do we show that A is a subset of C? We need to show that every element in A is an element of C. How do we show that every element of A is an element of C? We pick an arbitrary element of A and show that that element's in C. So let X be an element of A. Since A is a subset of B, then X is in B. Right? Because A is a subset of B means everything in A is in B. Since B is a subset of C, then X is an element of C. Therefore, for all X in A, then X is in C. Therefore, A is a subset of C. Good? Using the definitions directly, we show that every element of A is an element of C. That's how we show that A is a subset of C. Alright. This one was one where we disproved. If A is an element in B and B is a subset of C, then A is a subset of C is not necessarily true. Let's come up with a case. A is equal to the set containing 1, B is equal to the set containing the set. Said that wrong, or I was about to. B is equal to the set containing the set containing 1, and C is equal to the same thing as B. Right? So then we have A's in B, yep, that's true. B is a subset of C, yep, that's true. But A is not in C. So we came up with an example where it doesn't work. Does that make sense? That's how you disprove a statement. You find a case where it doesn't work. Proof by counterexample is what we call it. Alright, next one. Prove if A is in B and B is a subset of C, then A is in C. Let A, B, and C be set such that A is in B and B is a subset of C. Since B is a subset of C, then for all X in B, X is in C. Since A is in B, A is in C. We're done. Does that make sense? No questions? Alright. Next, moving on to D on 10.7. If A is in B and B is in C, then A is in C. And obviously that's not true. Right?
No.
So here's what we're disproving. If A is in B and B is in C, then A in C is not necessarily true. 1. Let's see. Let A equal the set containing 1. B equal the set containing the set. Well, that's going to be crazy with brackets. Let's start A equal to the empty set. B can be equal to the set containing the empty set. And then C is equal to with a set containing the set containing the empty set. 2. Then A is in B and B is in C, but A is not in C. And we're done. Came up with an example where that doesn't work, so that statement's not always true. Does that make sense?
So A is not in C?
Yeah. What are all the elements in C? Let's see what's in C. It has a set containing the empty set, and that's it.
So A has no relation to C.
Well, we haven't defined a relation yet. Oh yeah, we did.
Last week.
So I don't know what you mean by that. Is the relation A in C true in this case? No. There's no member in C that is A. What are all the things in C? The set containing the empty set. Good? Okay. Here's our calculus.
I was hoping that was
Yeah.
like, please say we're not like that.
No, that's a bit abstract for this class.
Yeah.
You're not really that kind. Get you through discrete math. Anyway, I'll see you next year.
Yeah, we'll see how this year goes. If I can get through this year and understand it all.
Even if you can't, what does that mean? Oh, I'm struggling with math, avoid math.
No.
Oh, I'm struggling with math, better take more math. And then we'll see you next year.
Yes, but if I try to enact this, I don't understand discrete math, how well is that going to turn out?
Well, you'll learn more math taking calculus than not taking calculus.
Yeah, I'm planning to take it.
And if you struggle with anything in college, it's going to be a math class.
Oh, yeah.
So, get comfortable with math. All right. What number were we on? 10.8? 10.8. Let A and B be sets. Prove that A equals B if and only if A is a subset of B and B is a subset of A.
Okay, how can it be the...
Is just stupid easy if you just use the definitions directly. So let's see. We're doing a proof. Well, we'll say it this way. A is a subset of B, and B is a subset of A, if and only if A is equal to B. Right? We're saying this implies this, and this implies this. Now you don't get to just say, obviously since they're subsets of each other, then they're equal to each other. Well, no joke. They wouldn't have asked you to prove it if that wasn't the case. And the reason that they're giving you obvious proofs to begin with is to get you comfortable with proving things that are obvious to your intuition. So let's do it. When we do if and only if proof, we need to show this implies this and this implies this. Right? So we'll do this direction first. 1. Let A, B be sets such that A is a subset of B and B is a subset of A. That's a B, not a 13.
13 is a subset of A.
Could be, you don't know. Alright. 2. Since A is a subset of B, then for all x in A, x is in B. 3. Since B is a subset of A, then for all y in B, y is in A. 4. Therefore, A is equal to B. We have our definition of what it means for two sets to be equal. A is equal to B if and only if for all x in A, x is in B, and for all y in B, y is in A. This is the definition of what it means to be equal. If you would have looked up in your book, what does it mean for them to be equal, wrote out the definition of what it means for them to be equal, you're done. That's how easy this is. You just plug in the definition. Which is why they give you proofs like this.
Why do we just overcomplicate it so much?
We're just dumb.
You're sitting there trying to come up with your own way of explaining with your own ideas about what it
Because
means.
that's what we think it's freaking saying. We think that it's saying, use your freaking logic.
Well, you do use your logic, but you also need to use very precise language.
I know.
Very precise definitions.
It's the worst.
If you ever say something like, you can tell, no. Definition, exactly what it means. This is exactly what it means.
Right.
Every word is chosen carefully when they give a definition. Now we prove it the other way. The other way is stupid easy as well. Oh, what are we on 5? Let A, B be sets such that A is equal to B. 6. Since A is equal to B, comma, then for all x in A, x is in B. Maybe put.
Yeah, that's right.
That's how I'd say it.
Alright. X is in B. Therefore, if we really want to be verbose, A is a subset of B. 8. Since B is equal to A, if we want to change up the order to keep the same logical flow, then for all y in B, y is in A. 9. Therefore, B is a subset of A. And we're done.
Cool. The end. Moving on.
That's what that proof looks like.
Wait, what's what we? Oh, 10.8.
Thanks. So 10.9, let A, B, and C be sets, and suppose A is a subset of B, B is a subset of C, and C is a subset of A. Prove A is equal to C.
So why did you say that I should have said of here instead of is in?
You're going to need to see your exact language. Since A is a subset of B, then every element, I meant to cross out that as well.
Okay.
Every element of A.
Okay. Because I'm thinking that of A.
Yeah,
Does that
sorry.
make sense?
Okay, so the next one. 10.9. If A is a subset of B, B is a subset of C, and C is a subset of A, prove that A equals C.
We.
A is a subset of B, B is a subset of C, and C is a subset of A. Then A is equal to C. So how are we going to prove that A is equal to C?
Every element in A is in C.
We need to show that every element in A is in C, and every element of C is in A. Now I was really generous with you guys on this one, because I felt like I was a little harsh with you on this one, and gave you all sorts of points that you didn't deserve.
Wait, what? You were saying you were easy on us on 8 and hard on us on 9?
Like I said, I thought I was a little harsh on you on this one, so on the next one I just have to be a little bit nicer.
Didn't I do this right?
I know I didn't do it right in the game before.
No, remember your individual stuff. Okay. Let's see. What was I doing? Oh, I have it right. Who cares what? Okay, so here's what we're trying to prove.
Right.
So,
So 1.
1. Let A, B, and C be set such that A is a subset of B,
B is a subset of C.
B is a subset of C,
A is a
and
subset.
A is a subset, or C is a subset of A, right?
Doesn't matter.
Yes!
It does matter.
Oh, yes, it
Matters
does.
very
I'm
much.
Sorry, yeah.
Okay, 2. Let X in A.
X and A.
Yeah, take an element out of A. And I need to show that thing's in C. And then when I'm done with that, I need to take an element out of C and show that thing's an A.
So why do we say let? Like, why not say like suppose or
Suppose
consider?
X is an A, same thing.
Yeah, but it's just maybe it's just the way I speak, but it doesn't make.
Why does that not make sense to me?
Let X be a member of A.
Okay. Okay.
Let X be an element of A.
Yeah, why do we have to do that?
So I need to show that A and C are equal. How do I do that? I take something out of A, and I show that it's in C.
All X in A is in B.
Here's where I'm trying to get. A is equal to C.
Right.
How do I get there? I show that everything in here is
So
in
you're
here.
trying to skip some steps?
No.
Then why not do that to that? It's almost the exact same thing.
You're saying
How do
this?
you never follow my freaking words? I swear. So frustrating. Okay, go on.
Alright, so let X be a member of A. We're grabbing some arbitrary element in A, and show me how you can prove that that element is also in C. Let X in A. Since A is a subset of B, then X is in B. Since B is a subset of C, then X is in C.
I see.
Therefore, A is a subset of C.
Okay, that's not what we're trying to show though. Okay, yeah.
Well, I'm going to show that A is a subset of C and then C is a subset of A. I'm going to use this. 6. Now we need to grab a random element in C and show it's in A. Let Y in C. Right? 7. Since C is a subset of A, right? Since C sub is a subset of A, then Y is in A. 8. Therefore, C, I don't even need that.
Yeah, you don't.
Overthinking it. We already know that C is a subset of A.
Yeah.
So I'll get rid of all that mess I was making. Since C is, and it makes sense why they gave this to you right after they gave you
Right,
this.
yeah.
Since C is a subset of A, and A is a subset of C, then C is equal to A. And we're done.
You don't even need step 6.
Alright. Thanks. There we go.
Are you just obsessed with those boxes or something?
That's what you put at the
Yeah,
end of your proof.
Silly. I'm not disrespecting you, I'm sorry, it's great. I started doing it.
Now, it's like, I was trying to think of a good analogy of something that we do like that.
Good period at the end of the sentence.
Kind of, but that one has
More use. It's
more use.
Yeah.
Yeah, it's more applicable when you're reading a textbook and you see it come up over and over again.
I see.
The end of the book.
Okay. More like it's closing braces to this thing. I don't want to think in terms of code.
Oh.
Here's where I started, here's where I ended it. Anything after this isn't applicable to this. Now I also number my proof so it makes it very clear where it ends. But that's not very common. Most people just write it as a paragraph.
Yeah.
So. And if it went on for several paragraphs, the box would demonstrate when the proof ended. Okay, anyways. How do I keep getting on a different page? Oh, you like touching it. And then 10.10 was the last one? Right?
Yes.
Yeah.
Shoot right here, I guess.
Can't believe we're in our 7th week.
Time flies when you're having fun.
Yeah.
All right. So,
A subset of B. Wait, no?
10.10? Was that my homework problem?
It was.
Okay, but you shouldn't write that.
If this, then.
It's just saying let.
Right, that's the same as the if.
So you might as well write down 1 and 2.
Well, I need to say what I'm proving. I need to prove that if A is equal to the set of all integers such that 4 divides it, and B is equal to the set of all integers such that 2 divides it, or is even 2 divides it. Then A is a subset of B. That's what we're proving. If this is true, then this is true. Alright. 1. Let A equal blah 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 when I wrote it there, and B equal blah 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 when I wrote it there. Okay? How do I show that A is a subset of B? I need to show that everything that's in A is in B. That's the definition of a subset, right?
Do that though. Make this one.
Let X be some element of A. Alright, if X is an element of A, or maybe we won't use X since we used X up there, maybe we'll use Y. Take some element of A. If Y is an element of A, what do we know about Y?
It's an integer and 4 divides it.
Yeah, it's divisible by 4. Since Y is in A, comma, then there must exist some integer, call it little a,
So Y equals.
such that Y equals 4A. Right? That's what it means for Y to be a member of the set A. It's divisible by 4. Or 4 times something gives you Y. Then,
So I had the right thinking.
well, I don't know. Then Y equals 2 times 2A.
Okay, yeah, okay.
5. Then 2 divides Y. 6. Therefore, Y is in B. 7. Therefore, A is a subset of B. Show that every element in A is also in B. Once again, you'll notice we're using the definition of subset and the definition of divides. Good? And I think that was all your 10 homework. Now, here's what I will let you do. I will let you resubmit your section 10 homework next week if you want, to go back and fix it. But I don't want you to write over your currently existing paper.
You must rewrite the entire homework.
If you want to, rewrite the problems that you got docked on, and then you would submit to me your revised homework along with my graded homework, so I know which ones you missed, and I can give you a better grade for that.
Okay, so we're just rewriting the ones we missed.
Yeah.
Are you
can
saying
just-
homework 4?
No, I'm saying section 10
So,
of whatever homework it's in. So you would have to re-give me homework 4 with your changes to section 10 in there.
Okay.
And then I could regrade it with your changes.
because we
And you
have
could boost your score.
Cool,
all
thanks.
the answers.
Then you have no excuse
Yeah, I'm wondering like what is
to make sure that you understand it.
He's not saying go and copy.
No, what I'm
it.
saying is like a lot of things you can write on paper, so I would just be copying down what you wrote already there. You see what I'm saying?
Well, if I were you, I would go reread the problem, see if you can redo it. So look where you missed,
Right.
reread the problem, see if you can redo it without looking at my notes.
Right.
And if you can do that, you're on a good track. I mean, if you want, you can just go look at what I did in the video and you can write it down that way. But the reason I'm doing this is because I'm trying to tell you very clearly, if you don't understand this, like, it's just obvious everything on this board. you're in trouble down the road. So cheating is just going to kill you down the road. So yeah, you can cheat if you want to, but if I were you, I would reread it, see if you can reproduce the proof without looking at my stuff, and then look at my stuff only to help you. Does that make sense? Okay. Now, section 12. Plus that way I'm guaranteed 3 views on my video. If I get those views.
You already do that.
Waiting for the day I hit those triple digits, you know. But double digits is a good start. Okay. I don't know what I signed for you on section 12, so can someone pull out their syllabus?
I have it.
Okay. Or I guess you can just look at your home and see what comes next.
You can.
So we start with 12.1 through 12.3.
No, 12.5.
12.1.
Through 12.3, and then you do 12.5. So you don't do 12.4. Alright. 12.1. Did anyone miss this one?
No.
Because I think you guys kind of got for the most part. I think maybe there was one question about E. So I think you understood A, B, C, and D, okay? But let's go over E. So we had that A was equal to the set 1, 2, 3, 4, 5. And by the way, if you redo the homework and you turn it to me, I will not be nice about anything.
Right.
Okay. Now expect that you understand everything you did wrong, you can do it perfect. B, 4, 5, 6, 7. So we were just writing down the different combinations, A union B, A intersects B, A minus B, B minus A. And then E was the symmetric difference of A and B. Now remember what this is equal to. This is equal to A minus B union B minus A. That's how we define that symbol.
The
So,
triangle?
yeah. So A minus B, this set right here is the set. A minus B leaves us with 1, 2, 3. And we're unioning that with B minus A leaves us with 6, 7.
Which is C and D.
So it's 1, 2, 3, 6, 7 is the answer. The second thing, 1, 2, 3, 6, 7, right? So that's your answer. And then the cross products, I don't think that there was anything that you guys didn't understand about those. Set of all the ordered pairs where the first elements A, the second elements B, and then vice versa. The only thing that I need to specify is it's a set of ordered pairs, not a set containing a huge multiplication problem.
I swear I put my comments in there.
Yeah, I just wrote over it.
Yeah, you just.
Okay. 12.2, more interesting one. 12.2. So we've got that the size of A equals 10 and the size of B equals 7. Now that should already be screaming at you one of the proofs we did. The size of A plus the size of B is equal to the size of the union of A and B plus the size of the intersection of A and B. So 12.2 says, let A and B be sets with the size of A equal to 10 and the size of B equal to 7. Calculate the size of A union B plus the size of A intersect B. Calculate this. What is this plus this? It's just 17. Right? Notice you didn't need to know what the size of this was exactly. You didn't need to know what the size of this was exactly. Maybe this is 17, maybe this is 0. Maybe this is 11, maybe this is 6. but the sum of them is for sure 17. No question there. It is impossible for you to come up with two sets, one of size 10, one of size 7, so that this does not come out to 17. You can't do it. That will always be the case. Any questions on that one? Alright, and then 12.3. Let A and B be sets with the size of A equal to 10 and the size of B equal to 7. What can you say about the size of A union B? So once again, we have the size of A is equal to 10 and the size of B is equal to 7. What can we say about the size of A union B? We know that this is between 10 and 17. That's what we know about it. How do we know that? If A and B have no elements in common, then their union is 17. If A and B have all their elements in common, as many as they can, which is all the elements of B are also in A,
Right.
then the size of their union is 10. So the size of the union has to be between 10 and 17. Similarly, the size of the intersection has to be between 0 and 7. 0 if they have no elements in common. 7 if all of B is in A. Does that make sense? That's really what I was trying to get the heart of. I know some of you guys had problems like figuring out what it meant by the x and the y. But in the first case, x is 10, y is 17. In the second case, x is 0, y is 7. That's all it was asking you for. Upper bounds and lower bounds on these two numbers. And I just wanted examples where this was the case. When is this the case? When is this 10? When B is a subset of A.
Yeah.
When is this 17? When A and B have no elements in common. Same exact thing here. When this is 17, this is 0. And when this is 10, this is 7. So the examples you use for this are also examples that work for this. When asked for those examples, they work for both. Everyone feel like they understand what 12.3 was asking for? Good? Okay. And then 12.5. Proof theorem 12.3. Don't you hate when it does that?
Yeah.
You have to go find the stupid problem.
Sure you do.
You want me to tell you what it is?
I know what it is, I just need to find it so I can write it exactly. 12.3, I really don't want to prove all these. Well, a better way of saying that is I don't want to use all the class time going through all these.
Yeah, we're gonna like not know homework.
Yeah, we're in trouble. So you have a good struggle ahead of you.
Yikes.
So let's pick one of the more convoluted ones. You had the one I did in class last time, right? So you have that in the fields, and you can go see what exactly I did there. So let's do one of the distributive ones. That's probably the harder ones. Do you guys have a preference? Which of those two you like?
The which ones?
A second?
The distributive? Okay, we'll do the second distributive one. By the way, when I said that you could redo homework 10, I meant 10 and 12. Because I really want you to understand sets. Very much. Okay. So, we're proving, you said the second one. We need to prove A intersect B union C is equal to A union B, oops, A intersect B, see my thinking wrong, but writing it right, union A intersect C, right? And as a side note, we know this can come back to logic. So thinking about Boolean algebra, how did we do x or y and z? We already proved that that was equal to x and y or x and z.
Did we use the truth table for
pretty sure we did, because we listed out all the different properties and we went over them that time. Make sure they made sense. Okay, so we're going to have to use this somewhere here. If you're not using that, you done messed up. Now, there's a couple ways that we can prove that these two things are equal. The insane way would be
supposed to be A union or A intersection, the first one?
A intersect B union C. Is A intersect B union A intersect C? Am I right?
So what about that second statement? Is that supposed to be X and? Because that says X.
Oh, jeez. X and Y or Z is X and Y. Sorry, I was reading it right in my brain, but wasn't reading what was written up there. Because this should make a ton of sense. If you have X and Y or Z, then you have X and Y, or you have X and Z. Right? So logic falls in. Okay, so there's the insane way to do this would be to take an element of that, show it's in there, take an element of that, show it's in there. You can be insane if you want. Or you can do it exactly like we did in class last time. We started with this and we kept manipulating it until it looked like this, using our definitions of unions and intersections. Right? So, 1. Observe that A intersect B union C is equal to the set of all X such that X is in A, and I'll use parentheses around my statements, and X is in B union C. As applying the definition of intersection directly. If X is
The other one.
the other
Well, yeah, just
distributive property,
symbol switch.
so you want this or you want that union, this intersection, this union, this intersection, this union. Now we're going to be showing X or Y and Z is X or Y and X or Z. Just flip all the symbols. So now a union B intersection C, the exact definition of that, is X is in A or X is in B intersection C. Right? And hopefully you can get there on your own. That's the exact definition of union.
Right.
Okay. What's that equal to? Well, now we need to plug in the definition of intersection right there. This is a set of all X, where X is in A, or X is in B, and X is in C. Now think about each one of these as a statement. X is in A is a statement. X is in B is a statement. X is in C is a statement. This has the exact form X such that, well, I'll call this statement X or statement Y and Z. This has that exact structure right there. And we're going to use that fact to restructure it this way. Remember, these are statements. They're either true or false. They have Boolean values. Our Boolean algebra applies. So this is equal to the set of all X such that, use our distributive property. So such that, this is what we're thinking about as X up there, this is what we're thinking about as Y up there, this is what we're thinking about as Z up there. You go with the connection I'm drawing? Okay. So then we have, using the distributive property, we have X is in A, X, or X is in B, Y, and X is in A, or X is in C. Distributive property. Right?
And you can just take it back out. But wait.
Now reverse your definitions. X is in A or X is in B is the same thing as
A union B.
X is in A union B. Perfect. And X is in A or X is in C is the same thing as X is in A union C.
Is that saying X is in A union C or X is in A union C?
Oh, sorry. The in comes after the set operation.
Okay.
That is a good point. I should have specified that better as I've been doing this. X is in the resulting set.
Okay.
Does that make sense? Sorry about that. And then once again, we have X is in this set and X is in this set. That's the definition of intersection. Oops. That was supposed to be Q. There we go.
Yeah, so nice.
I probably shouldn't have written this line. Could have gone from here to here.
Yeah.
And then you can put that line. But that's it. Apply the definition. Apply the definition again. Distributive property. Back to the definition. Back to the definition. I can't think of better proofs to have you just get comfortable plugging in definitions. Good? So you guys can finish those ones out. Right? Do you feel like you can do the rest of them now?
Well, yeah.
Probably.
I did pretty good on this section. No, I didn't.
Wait, what's the one?
I thought I did pretty good on this section.
Okay, so what number did we just do?
12.5.
Okay, so now we're looking at 12.7. 12.7, let A and B be sets. Explain why A intersect B. Wait, I read the wrong one. Did I? What am I looking at? 12.7. 12.7, sorry. Early, we presented a Venn diagram of the distributive property. Please give a Venn diagram of the other distributive property. That one, I think, is pretty obvious to you if you see the picture. But we'll write it down real quick. Crap, I lost it again. 12.7. So we're given a Venn diagram of A intersect B union C. And A intersect B, union A intersect C. And the point is to pictorially see that these two things talk about the same thing. Now I'm not going to drop all the things leading up to the picture, I'll just skip straight to the point. So we'll call this A, we'll call this B, we'll call this C. So we want everything that's in A and into B union C. That's this. That's everything that's in A. That's also part of B union C. B union C is all of B and all of C together. What's all that? That's also in A. It's that. Good? Let's do it over here. We need everything that's in A intersect B. That's this. Union with everything in A intersect C. That's this. Union those together. Whoa, we got the same thing. Surprise, surprise, distributive property works. Okay. That was 12.7. Next is 12.11. Let A and B be sets. Prove or disprove A union B is equal to A intersect B if and only if A equals B. And is that true?
Yeah.
So then we got to prove it. And there's two ways that we could do this proof. One of the ways we can do it is with the cardinality of the proof. Or the cardinality of the sets. But we'll do it directly. What number were we? 12.11?
Yeah.
So, prove A union B equals A intersect B if A equals B. Sorry, I'm thinking about a different way of proving it, but I don't have a well formula in my mind, so I'll continue this way. Okay, if and only if proofs. We gotta show the left implies the right and the right implies the left. Start by going this way. 1. Let A be. Oh, we only have 2 sets. Let A and B be sets such that A union B is equal to A intersect B. Right? How do we want to do this?
Give the definitions of it.
Yeah, pick something
What's
A,
the
show that it's
definition
in
of
B.
A union B?
A union B is everything that's in there or there. And A intersect B is everything that's in there and there.
Okay.
So let X in A. Pick some element. Since X is in A, X is in A union B, right? Since X is in A union B, X is in A intersect B. Since X is in A intersect B, X is in B. Right? And then we can do the exact same thinking for showing that something in B is in A. Is there any part of this that's weird? If X is in A, then it's in A or B.
Okay, got it there.
A or B is the same thing as A and B. So if X is in A or B, that's the same thing as X being in A. Oh.
Okay.
Oh yeah, since that, then that. Okay, I did that right. So since it's in there, it's in there. Those two are equal.
Okay. Okay. Yeah, that makes sense.
And then since X is in A and B, X is in B.
Okay.
Follow the logic there? Is there a part of it that feels weird?
I feel like A union B equals A intersect B if and only if A equals B. I feel like we can't prove that until we prove that A equals B.
I need to show if this is true, then this is true. And then if this is true, this is true. So I'm assuming A and B are set such that this is true.
Right, I know you have to do both. I'm just saying it feels like it would make more sense if you did A equals B first.
Well, either way I've got to do both. So do you have a problem with the actual proof that's up here though? Is there something weird?
Just because that little sentence right there, but it's fine. Because I feel like we have to assume that that's true to prove it.
We have to assume that this is true?
No. A union B equals A. Right.
We have to assume that this
Prove
is
that
true.
it's true when we have A equals B.
We will.
Right.
But that's not the way we're doing it.
But this.
We're proving that this is true when this is true. So now I'll do the other thing. Let A and B be sets such that A is equal to B. 7. Now we need to show, oops, I kind of didn't finish this.
Oh yeah. one last step.
Since X is in that, then X is in B, right? And then we can do the exact same thinking reversed to show that if X is in B, then X is in A. If X is in B, X is in that, which means X is in that, X is in that. I'm kind of saying that for a time. Do you see how to reverse it? Is it obvious? Or should we write it?
No, it's obvious how to reverse it, but.
So all I showed so
that
far.
first proof was proving A equals B.
Alright, let's just.
Was it not?
6. Therefore, A is a subset of B. That's what this is proven so far. And then similarly,
If
you
reverse
prove.
it,
Yeah.
then B is a subset of A, subset A equals B, right?
Similarly, B is a subset of A. So A is equal to B. That's what we're so far. Now let's start this. Let A and B be sets such that A equals B. 9. Let X be an element in A union B. This is a lot more straightforward.
No. Start with A as a subset of B.
What?
Because you know that A equals B. So then you know. Hang on. Oh, okay, never mind. I see what you're doing. You're doing the exact same thing.
Just reverse.
Yeah, but this one we might be able to do even easier.
Well, I think what she's thinking is,
I think I can actually just go like this.
if A is B, then you can say that A is a subset of B and B is a subset of A. And then go backward from there.
Let's just do that and call it good. If A and B are equal, A union B is the same thing as A union A, because A and B are equal.
Okay.
It's the same thing as A. It's the same thing as A intersect A. Same thing as A intersect B.
That makes sense.
Let's just do that.
Huh?
That's pretty quick.
Yeah.
Oh, I see, yeah. Ow. Yeah.
So there, we're done. We proved it both ways.
Interesting.
What's next? I lost track of the number.
12.21.
12.21. True or false? For each of the following statements, determine whether the statement is true or false and then prove your assertion. That is, for each true statement, please apply a proof, and for each false statement, present a counterexample with explanation. So A, B, and C are sets. So we don't need to prove each one of these, I think we can just explain it when they're false. So A minus B minus C equal to A minus B minus C. No, no, no. Maybe we're going to have to write these out as we go. I've already have a thing here. So this is 1221. A minus B minus C equal to A minus B minus C. Okay, let's think for a second when all of these are equal. Pretend set A is equal to set B is equal to set C. Okay? What's B minus C?
0.
The empty set. So we have A minus the empty set, which is just A. Now let's look at over here. What's A minus B?
Same set.
The empty set minus C is the empty set. Those are not the same thing.
Huh.
So
Wait, how do you
But
take
it
an
works
empty
with
set
a
minus
plus,
C?
right?
we don't have a concept of plus two sets. That's not a thing.
What are you talking about? They're not
Set A plus set B.
So-
Yeah, they are. They're sets.
I'm just trying to.
Did you not realize that you were talking about sets?
Probably, yeah.
In the following, A, B, and C denote sets.
Mhm.
Yeah. Well, that explains why we got for them. So, any questions on that? See how those are not the same thing? So, set subtraction is not associative. Union was, intersection was, set subtraction, no, not associative. B. A minus B minus C equal to A minus C minus B. Let me make sure I write that right. A minus B minus C equal to A minus C minus B. These two are equal. We have A, we get rid of everything in B, then we get rid of everything in C. We have A, we get rid of everything in C, then we get rid of everything in B. So this is a set of all things in A, not in B, not in C. This is a set of all things in A, not in C, not in B. They're the same set. Good? Okay. What were we on?
C, put up 1221.
1221. C.
We were supposed to prove all these, right?
Yeah.
Okay, just want to make
So you just say, observe that this is equal to the set of all x in A and not in B and not in C. This is equal to the set of all x in A and not in C and not in B. Use your properties on logic, and you're good to go.
I just overcomplicate things so much. 10 steps to do that.
Okay. C. We have A union B. And you have definitions of what exactly these are every time we introduce a symbol. We give an exact definition. So you can plug into the exact definitions of what exactly these sets are and write those out in set building notation like we did on piece I erased. Oops. Yeah, got rid of it. Anyways. A union B minus C equal to A minus C intersect B minus C. Let's think, is this statement true? My gut says no, I'm trying to think of a case where it doesn't work.
It should be true. Marked as right when I proved it.
You marked it as
A
wrong.
union B minus C. Everything in A or B, not in C. Everything in A and C, maybe the one right under it uses a union and it's correct. Shoot, we're on C. A union B minus C, A minus C, and B minus C. Oh, I think my thinking was make A and C the same set and B a different set. That's how you do it. So you have A, so you think about A is equal to B is not equal to C, is all you need to think about for this, and we can do it. So A union B is just A, minus C is whatever it is. Over here, A minus C is just whatever it is. But then we intersect that with B minus C. Oh, oops. That doesn't work like I thought. A union B minus C equal to A minus C intersect B minus C. Alright, then let's just give sets to it. A equal to the set containing 1. B equal to the set containing 2. Yeah, it's not true. I know it's not true. I can see that. I'm just trying to come up with an example. And we'll do C equal to one of these. C equals 1. Oh, that's how it's equal. C equal to one of them different. Alright, so we'll use this example. C and A are equal to the set containing 1, B is equal to the set containing 2. So this set is a set 1, 2, and we're minusing the set 1, which just leaves us a set 2, right? Over here we have A minus C is the empty set, intersect anything is the empty set. Right?
Uh-huh.
B minus C over here is just 2.
Well, no, it would be 2.
That intersect the empty set.
Intersect.
That's what I was saying, if that was a union, it would be true, but it's intersect. So there you go, an example where it's not true. Are there questions about that?
No.
D. B equals A union C, union, that's not important, implies A equal B minus C.
No,
Oh, did I read that wrong?
we're doing D, not E.
Oh, oops. If A equals B minus C,
Then B equals A union C.
then B equals A union C. So let's think about this one. It's false. So let's think about a case where it's true. Make B equal to C and A something else. Oh, we can't because we have to make them equal over here. If A equals B minus C, take B, get rid of everything
Why
in
can't you
C.
put B equals A union C in the position of B on the other side?
You can. So you rewrite this as A equals A union C minus C. Right?
Good.
B equals A union C, substitute right there. So then, if you have that, so think about the case where, well, it's kind of a weird thing to do, but this doesn't give you backed out A,
Yeah.
because if that has overlap, that doesn't work. So it doesn't work when A and C have overlap but aren't the same, so let's create that real quick. So we'll make A equal 1, 2, C equal 2, 3, and then what does that make B equal?
1, 2, 3.
Oh, we can't do that. If A is equal to B minus C,
Or is it just 2?
here's what we really need to check. If we plug this in over here, it doesn't work. So B is equal to A union C, right? Oh, that is going to be true. Did I mark false on your paper?
Just mark the X when I said it's true.
Well, did you prove it?
But I did it the other
I
way.
proved it wrong, so you
Yeah,
marked
I
it wrong,
guess.
but you can say it was false.
I might have thought about it wrong when I was doing it, and I think thought about this and applying this. So let's think, if this is true, then this is true. If we plug in B minus C there, then yeah, that's just going to give us B. Because this is equal to the set of all x where x is in A and x is not in C, or x is in C. Oops, not A, B. Does that get us back to set B? No, because that could give us elements of C. Why do I keep thinking that this is true? No, it's false. It's definitely false.
So what's the counterexample?
It's definitely false, and so we need
Why don't we just plug in numbers for them?
B equal to
Oh, no, that's false.
C equal to, let's see, 2, 3 should work, right? And what does that make A equal? A equals B minus C. So B minus C makes A equal to the set
1, 3.
1, 3. Okay, so this should work. So A is equal to 1, 3,
You're gonna prove it though.
but I'm showing it's false. Here's the case where it's false.
Okay.
These numbers make the statement false.
Okay.
So I have A is equal to B minus C, that's true.
Oh, I see.
But is B equal to A union C?
No.
No. It's missing the 3. Okay, there's a counterexample.
Okay.
So it's not true. That's right. Pretty long of a day. Nice, some more space here. What was next?
E?
Yeah.
Is it?
E through.
E. If B equals A union C, then A equals B minus C.
Oh, so now it's opposite way.
Oh, yeah, so that one's got to be false as well, right?
What?
No?
No.
'Cause now that implies that.
These are different.
Why is that not true?
So let's see. Let's write it out. We're looking at E. I keep looking at both of them. So I need to show that B equals A union C implies
A equals B minus C.
A equals B minus C. So if this is true, is this necessarily true? Well, if that's true, then that means that A equals, substituting in for B, A union C minus C, which isn't going to be true. So how are we going to show that that's not true? We need A and C to have some overlap, and then it doesn't matter what B is. So A can be 1, 2. C can equal to 3. And then that makes A or B equal to 1, 2, 3, right? So we have B is equal to the union of A and C, that's true. But is A equal to B minus C? Does A equal
Yes.
B minus C?
No.
No.
Frustrating.
Okay, then why did you?
Did I call it true on yours?
Yeah.
Yeah, because I got confused and shouldn't have.
That's fine.
Did I mark it true on yours and false on your guys'?
Yeah.
You said you put a check mark next to it.
Well, you got lucky, kid.
Oh no, I disproved it. Okay, we're good. Sorry, I thought I was proving it. No, I disproved it. Okay.
Well, good job.
So I did agree with it, right?
Okay.
Trying to remember what's that.
Alright, F.
F. F is obviously not true.
Wow, I got it right.
A minus B is not equal to the absolute value of A minus the absolute value of B. Or is it?
So all these are.
Not. Promise you.
Dude, maybe this one is true.
No, it's not.
The size of A minus B
It's not.
is equal to the size of A minus the size of B.
Okay.
Right, no, it's not true because they could have no overlap.
Yeah.
Yeah.
Right, so if A is equal to the set 1 and B is equal to the set 2. And the size of A minus B
That
is
doesn't
1.
matter, that's 1 and 1.
1 minus 1, you get 0 over here and 1 over here.
1 minus 1.
What's the size of A?
Oh, the size of A minus B. What's B?
17.2.
So B is 2.
No, it's a set containing 2. It's a set. So what's a set containing 1 minus a set containing 2?
Maybe more. I have no idea. Why would I know?
The set, because we went over it. I guess we skipped that one here, kind of.
How?
What's A minus B? 1, 2, 3. What is the set containing 1 minus the set containing 2?
0.
Is that containing
What?
1?
What are you talking about?
How do one of these make sense and not the other? Let's go back to this one. This one makes sense to you?
Yes.
So when I say A minus B, then that's 1, 2, 3.
6, 7.
No, that's the symmetric difference. I'm saying just A minus B.
Okay, hang on 1 second. Yes, okay.
So A minus B is just 1, 2, 3. So the set containing 1 minus the set containing 2 is just the set containing 1. So this has size 1, and this has size 0. And 1 is not equal to 0.
Okay.
Make sense?
Yeah, sure.
Well, it does or doesn't. Sure, I don't know what that means.
Well, I got it right, so.
Sometimes it like makes sense, but you're still unsure about it.
Yeah.
A minus B union B, we already know is false. We already did something that looked a lot like that. Can you see an example of that?
No.
You just make sure A and B have some overlap,
Okay.
but not all overlap.
H is false.
And then H, same thing.
No.
Oh, they changed the order.
No, it's not the same thing.
Huh?
It's not the same thing.
It's really close to. But it's also false. You just make sure A and B have some overlap, but not all overlap. So then both those make A equal to 1, 2, and B equal to 2, 3. And you're good. Okay. And then the last one was 12.22, which we did before the test. Right?
I think so.
Yeah, we did. So we already went over 12.22.
Okay, great. Alright, can we start now?
So that was review from your homework.
Okay, wait. Oh, yeah, okay.
So we're done with that. So go on break. When you come back, we'll start new material. See how far we got.
What happens if we don't get all the way
Then
done?
we
You
try.
So our homework just becomes way harder.
You better show up after school to get help, I guess.
Okay.
I just do the problems that I did wrong?
Just turn in all your homework again, but also include the problem that you did wrong. All right. You ready?
It's ready as I want to be.
You ready? Get back here more focused on your homework. Just a suspicion. See, the reason I need you to get better at sets was so that this stuff would make sense.
Well, go up, let me practice it, and then we take 3 days.
Well, if something doesn't make sense to you, then you should be able to count it. Okay, so first off, this section introduces 2 other ideas that are going to not go away. They're going to be in all the sections from here on out for the most part. And that's the idea of an equivalence relation and of this crazy mod n type stuff. So let's jump into it. An equivalence relation. You remember talking about relations last time? What's a relation? A set of ordered pairs. Wonderful. I don't have to yell at you. A relation is a set of ordered pairs. And we talked about 5 different properties that a relation can have that we're often interested in. A relation can be reflexive. What does it mean for a relation to be reflexive?
X relates X.
Yeah, all elements are related to themselves. Irreflexive, which meant
It never relates to
it's never related to itself. Symmetric, which meant,
This is related to this, then that's the other way around.
yeah, X is related to Y, then Y is related to X.
Right.
And then we had anti-symmetric. That's the really weird one.
Which is if that is the case, then X equals Y.
Right, if the relation's symmetric, then X is equal to Y.
Why do they call it anti-symmetric?
Why do they call it irreflexive?
I don't know.
Neither do I.
No, that makes sense. Irreflexive?
'Cause
It's
not-
possible for it to not be reflexive and still not be irreflexive. Reflexive means always related to itself. Irreflexive means never related to itself. If it's only sometimes related to itself, it's neither. So yeah. Let's think. And then transitive. What was transitive?
If X is equal to Y and Y is equal to Z, then X is equal to Z.
Almost. Every time it said equals, replace related.
Right.
If X is related to Y, Y is related to Z, then X is related to Z. Perfect. So those were the 5 properties that relations often have. 3 of those properties, we're very interested when relations have 3 of those properties specifically, meaning reflexive, symmetric, and transitive. If they are reflexive, symmetric, and transitive, we call them an equivalence relation. And these things come up all over the place. For example, so let's read the exact definition, make sure it makes sense. Let R be a relational on a set A. We say that R is an equivalence relation provided R is reflexive, symmetric, and transitive. Makes good sense? Yeah? Yeah? No? You with us?
Sure.
Sure. That's not very convincing.
My brain is so active.
Well, let's get it with it, and then let's make it make sense. Michael Scott wasn't right when he says the brain tells the body what to do. Or the brain tells the mind what to do. Anyways, so let's look at some examples of equivalence relations that you've come across already. Congruence in geometry is an equivalence relation. In fact, that is one of the axioms of geometry.
What's an axiom? Like you've said it a lot, but none of us actually know what it is. Have you told us what it is?
I don't know.
Well, you told me a million times.
Yeah, I have told you a million times, plus you've done a real geometry class. Every field of mathematics looks like this. You start out with some basic assumptions. And then you look at the logical implications of those assumptions. If those are true, then what else is true?
So you have to start with assumptions, or
You always start with assumptions.
what are the assumptions? So does each field start with the same assumptions or different assumptions?
No, different assumptions. So the axioms of, and the axioms are those assumptions. We call them axioms.
Okay.
They're the basic assumptions that we make that we don't have proofs for. Because think about a proof. Anytime you prove something, it's of the form, if this is true, then this is true. It's always if then.
Right.
But we need our first ifs.
Mhm.
And our first ifs are those axioms. And so,
So what are the axioms of discrete math that we learned?
well, discrete math is playing with a few fields, so we don't go back to the exact axioms of the field, which is too bad.
What about algebra or geometry? Because we've taken those ones.
It depends on what you're doing. So, for example, you're doing algebra with real numbers. So the algebra on the real numbers, you can go back to the axioms that you use for that. And there's 10 field axioms, which, for example, some of them you already know. The associative property, the commutative property,
Those are
for,
axioms. Aren't
for
there proofs for that?
additions. How would you prove it?
Well, we proved it.
How would you prove that A plus B is equal to B plus A?
Show that they
sum to the same value, I guess.
How?
Well, no, that doesn't even, that doesn't work.
Yeah.
Well, what do you mean they sum to the same value? You're thinking, okay, plug in 3 here,
Yeah.
plus 7 is equal to 7 plus 3. You get 10 is equal to 10. Yeah, okay, you show an example where it works.
But you'd have to show up variables, which is like not possible.
And so it's a fundamental assumption of the real numbers that this is true. There's no proof for it.
So why do we have to prove that with sets?
Why did we prove that with sets?
Yeah, like a bunch of homework problems have been for Boolean algebra and for set relations.
Right, so we were able to base that in our algebra on Boolean. So we created a Boolean algebra, which is like developing logic. And then we were able to use the fact that and was commutative to show that intersection was commutative. And that and was associative to prove that commutativity was associative.
Okay.
And we were able to do that from truth tables. We were able to prove that for and. But this, no, you don't have to prove for it. So there's fundamental axioms. Fundamental axiom on geometry was, for example, that on any line there's 2 points. No proof of it. Just a fundamental assumption that you make.
Okay.
The assumptions are like the most basic things that you're just going to accept as true.
It just seems so obvious.
Because you have to start somewhere. And so the goal is to start with the things that feel just as obvious gets. That's the goal. And it's not even proven as obvious gets, because the axioms themselves we never say are true.
Well, that's
Right? We just say if they're true, then this is what it is. Because not all axioms agree with each other. So for example, in geometry, using Euclid's postulates, or axiom, same thing, postulate, axiom, same thing. Then there's one that basically says, if you have a line and a point not on the line, there's only one line I can draw through that point parallel to this line. That's a postulate. Now it turns out, if you say that there's more than one, you now went from Euclidean geometry to what's called hyperbolic geometry. And if you say that there isn't one, you now went from Euclidean geometry to elliptical geometry. Because there are geometries where there is no line I can draw through that point parallel to this line.
whether
There's
there isn't one, there literally isn't one.
There is, if you're talking about Euclidean geometry. So when you're looking at this whiteboard, which is a Euclidean surface, it's natural to appeal to your intuition that that's the case.
Right.
But, trying to give you some intuition another way, think about a horse's saddle. That's the kind of surface you think about for hyperbolic geometry. So a horse's saddle, if we look at it from the side, looks like this, right?
Okay.
And from a bird's eye view, we'll just, it's a rectangle looking down on it, right?
Okay.
So this is an idea of a hyperbolic surface. And what does it mean for two lines to be parallel? It means they don't intersect. Two lines never intersect, they're parallel lines.
Okay.
Right? So now, if you think about a line that I draw from, let's say I have a line right down the seam of the saddle. And I want to make a line parallel to that. Okay?
Okay.
So that's the line that we can barely see the top of right there, right down the seam of the saddle. Then, if I draw a line really, really close to it, and I draw it straight out like this, so you see that line right there. When you're looking down on the saddle on that line that I draw this way, that line's going to look something like this. Right? The distance from here to here is a lot bigger than the distance from here to here.
Right. Okay.
So, well, maybe I shouldn't have drawn it like that. That's confusing, because on a bird's eye view, it's still going to kind of look like this. But the distance between here and here is a lot bigger than the distance between here and here.
Right.
And so I could draw another line, like this, that's slanted, so that the distance between here and here is growing faster than this is getting closer to this.
So that's more than one.
Yeah, so here's another line. I draw another line through. And if the surface continued to infinity with the same curvature that it has right here, then the space between these lines grows faster than this line approaches this line. And I could draw infinitely many. I could draw another one and another one in between those. So in hyperbolic geometry, there's infinitely many lines. You can draw through a point parallel to a given line. And then elliptical geometry is like trying to draw lines on the surface of a globe. And you can't draw two lines that don't intersect, but you don't have good intuition for what lines are. In terms of the globe, that would be great circles. You can't have two great circles on a line that don't intersect.
Okay.
So we need two great circles intersect. So we need two lines intersect. So there's no parallel lines. So depending on which axiom you want to use dictates which geometry you're in. If I want to use the axiom that there's only one line, then I'm in Euclidean geometry. If I want to use the axiom that there's infinitely many lines, then I'm in hyperbolic geometry. If I want to use the axiom that there's no lines, then I'm in elliptical geometry. And so the axioms dictate the math that you're in, the field of math that you're in. It's not that one's true and one's false. It's not that one's really the truth and the other one's really false.
It just depends on your circumstances.
It's just that if one's true, then what else is true? That's all math cares about. If this is true, then what else is true? So what's true is the logical implication, not the statement itself. We never prove that A is true. We never prove that B is true. We prove over and over again that if A is true, then B is true. That's the truth that we're interested in. The fact that A implies B. That's what we say is for sure true. You can argue about whether or not A is true. You can argue about whether or not B is true. But no one can dispute the fact that if A, then B. The truth of that statement. That implication. And that's the kind of statements that mathematicians are interested in. Theorems. Does that make sense? So, that's an axiom. Good question. Okay, so back to our examples of congruence relations. I said one example of a congruence relation that you're familiar with is the idea of actual congruence in geometry. So you can think about triangle congruence if you want. What does it think about two triangles? Is a triangle always congruent to itself?
Yeah.
Yes. So it's reflexive. If triangle A is congruent to triangle B, is triangle B congruent to triangle A? Yes. So it's symmetric. If triangle A is congruent to triangle B and triangle B is congruent to triangle C, is triangle A congruent to triangle C? Yes. Another example would be the has the same size relation on sets. Does set A have the same size as itself? Yes. If set A has the same size as set B, does set B have the same size as set A? Yes. And then if set A has the same size as set B and set B has the same size as set C, does set A have the same size as set C? Yes. So congruence relations, they somehow capture this idea of they're somehow the same. So even if they're not exactly the same, they're somehow the same. Their ways that we capture properties are somehow the same. So even though the set 1, 2, 3 is far from equal to the set 4, 5, 6, these are congruent, or these are related under the has the same size relation. And so equivalence relations capture things that are somehow the same. If it's an equivalence relation, then two things are somehow the same. Even if we can't find exactly how they're the same. Just like these two are the same in size. Triangles, I mean, if I put a triangle here and I put a triangle here, those are very different objects. This is a set of points way over here, this is a set of points way over here. But congruence somehow captures the idea that they're the same. Does that make sense? So that's what they're intended to capture, is somehow these things are the same. These related things are the same. They have some common property. And equivalence relations capture those. Alright. So let's look at a specific equivalence relation that we're going to use over and over again, especially as we get to number 2. So let A be any positive integer, 1, 2, 3, 4, 5, etc. Then here's how you read this. We say that x is congruent to y modulo n, or x is congruent to y mod n. We hardly ever say modulo, we just say mod. So x is congruent to y mod n, provided n divides their difference. In other words, x is congruent to y mod n if and only if x and y differ by a multiple of n.
What's a modulo?
A remainder is what we typically think of mod. So, computer science terminology, 57 mod 5 is 2, because 57 divided by 5 has a remainder of 2.
Okay.
Does that make sense?
So mod and
You've been calculating mods since you were in, I don't know, 3rd grade, whenever you got introduced to division. It's the remainders. So what this is really saying is x and y have the same remainder when divided by n. That's another way you can view this.
Oh.
3 and 13 mod 5. Is 3 congruent to 13 mod 5? Do they have the same remainder when you divide it by 5?
Yeah.
Yeah, 3 divided by 5 has a remainder of 3. 13 divided by 5 is 2 with a remainder of 3. That's one way you can view it. Another way you can view it is there difference a multiple of 5? What's 13 subtract 3?
10.
Is that a multiple of 5? Then the statement's true. So that's another way you can think about it. The way I always think about it is, do they have the same remainder when I divide by that? That's how I think about it. The author suggests, well, this is the exact definition, so if you ever have to prove anything, this is what you use. Here's the definition exactly. But he also gives you this as a way to help you think about it. So let's do another one. Is 3 congruent to 1003 mod 5?
Yeah.
Yeah. Is 4 congruent to 4 mod 5?
Yeah.
Sure?
Yeah.
Okay. And then 16, is it congruent to 3 mod 5?
No, 16 mod 5 is 1.
Yeah.
Right? Is that
Yeah. Yeah, you're kind of skipping ahead to the mod
Is that what?
operation.
How do you say, what is, yeah, I'm not really sure. Like, I understand kind of what mod is, but not completely, so I'm not sure if I'm using it right.
You said that perfect. 16 mod 5 is 1, and 3 mod 5 is 3, so 16 is not equivalent to 3 mod 5. You said that exactly right. But we haven't introduced the idea of 16 mod 3 yet.
Okay.
So let's do some more. Tell me if it's true or false.
True.
False.
We got true, we got false, we need tiebreaker.
No, wait. False.
False.
Is this statement true or false? Is 3 congruent to 5 mod 2?
Wait a minute, no, it's true. That's true.
Is 3 congruent to 15 mod 2?
Yeah, that's true.
Yes? How do you know?
Both have remainder 1.
Both have remainder 1, that's what make you do it. Or 15 minus 3 is 12, is a multiple of 2.
Right.
Alright, next one. Is 0 congruent to negative 14 mod 2?
Yes.
You sure?
Let me check it.
Yeah, look at that definition. Read it, reread it, and then see how you feel about that one. 0 is congruent to negative 14 mod 2.
That can't be right. Wait.
Oh, yeah, that's right.
You sure?
So, if we have
How are you doing it in your head?
2 divides, negative 14
0
minus 0.
minus negative 14 is 0 plus 14.
Okay, is 14,
Yeah.
which is
Which is
multiple of 2.
the left
There you go. That's one way to do it. Or 0 divided by 2 is 0, remainder 0. Negative 14 divided by 2 is negative 7, remainder 0.
Right.
However you want. Alright, next one. Is 3 congruent to 12 mod 2?
No.
No. Is negative 1 congruent to 0 mod 2?
No.
Is 3 congruent to 3 mod 2?
Yes.
Yes.
You sure?
Why do you do that?
Yeah. To make sure you're sure. Alright. You're right. Now you'll notice, now that I pointed out to you, that the idea of mod 2 captures as the same parity. In other words, are they both odd or are they both even?
Well, mod 2 does.
Yeah, mod 2, that's what I'm saying.
Right.
So the answer was always true when they were both odd or both even. But if one was odd and one was even, the answer was false. Okay. So that's equivalence relations. Now we have the idea of an equivalence class. Oh, wait, no, I skipped a proof. Let's do the proof I was in the middle of writing. Oh, now I need to prove that this idea is a congruence relation. So I need to prove it's reflexive, it's symmetric, and it's transitive. So let's start with reflexive. Well, let's just make sure we understand what I'm doing so far. So the congruence mod n is what I'm calling that relation, is an equivalence relation on the set of integers. That's what I'm proving. Okay? You understand what I'm proving? You understand what I need to do? I need to show it's reflexive, symmetric, and transitive.
So
I
what?
don't
Okay, so
understand it.
what I'm not understanding is congruence mod n. What? I don't. Think
That means this. Right here. That's capturing this idea.
Oh,
So is x congruent to x mod n?
so that's just congruent mod n.
Yeah, congruence mod n is
What?
how we refer to this.
You're speaking Spanish right now.
This, alright. The way we read this is x is congruent to y mod n.
Right, okay.
So we call this the congruence mod n relation.
Okay.
If x
Oh.
is congruent to y mod n, then it's in the relation. If x is not congruent to y mod n, it's not in the relation. Okay? So we're proving that this is a reflexive relation, or equivalence relation. First off, we need to prove it's reflexive. So I need to show that for any integer, x is congruent to x mod n. I need to show that this statement is always true. Oops.
I kind of understand what that's saying, but like.
Well, what is this saying? What's its exact definition? That means that n divides x minus x. What does that mean? That means n divides 0.
Which it does.
What does that mean? That means n times 0 equals 0. Ah! And then go backwards. Didn't have to erase my train of thought. I'll work backwards here. Observe that n times 0 is equal to 0, which gives us that n divides 0, which gives us that n divides x minus x, which gives us that x is congruent to x mod n. Or, therefore, it's reflexive. That was weird. Whatever I see. Therefore, it's reflexive. Now, switch out my markers and show that it is symmetric. How do we show it's symmetric? We need to show that if x is congruent to y, then y is congruent to x, right?
Okay.
So 5. Let x and y be integers such that x is congruent to y mod n.
I understand what you're trying to prove, but I'm struggling with, for some reason, how to work with the mod n. Like, I understand even what the mod n is.
Oh, I probably didn't specify that here. N is just a positive integer. We're saying that this is always true no matter what n is. N can be 2, n can be 5, n can be any positive integer. This is always the case.
So I even put it there.
I need to show that this is an equivalence relation. I need to show that no matter what n is, x is always related to x. X is always congruent to x mod n, no matter what n is.
Okay, now it's new. Okay.
That means it's reflexive. Then I need to show if x is congruent to y mod n, then y is congruent to x mod n. That means it's symmetric. Then I need to show if x is congruent to y mod n and y is congruent to z mod n, x is congruent to z mod n. I feel like you guys were really getting this and suddenly dropped off.
I was really getting it, but I don't get it
You're getting
anymore.
it just fine. We'll move on.
Well, let's get those who weren't. Go back to this. How did you know that 3 was congruent to 13 mod 5?
Because when you divide 3 by 5, it's 0, remainder 3. And the remainders are equal.
The remainders are equal, that's one way to do it, or their difference is a multiple of 5. Right?
Okay?
Which is the exact definition.
So what we're saying here is x is congruent to y when y minus x is a multiple event. Kind of.
Yeah, x is congruent to y mod n. What does that mean?
Y minus x is divisible by n.
Then n divides x minus y.
Okay? I thought it was y minus x.
Oh, let me see. X minus
x
y.
minus y, okay.
So then n divides x minus y,
Okay.
which gives us that n is equal to, trying to get to skip a step here. N is equal to a some integer times x minus y, right?
Alright.
Which then gives us that n is equal to negative a times y minus x. Pull out the negative.
Okay. Why do we do that?
Well, which gives us that n divides y minus x.
Ah. And that shows that there's
Which gives us that y is congruent to x mod n. Any question on that line of thinking?
Yes.
Alright. Where do we start?
Very first.
Alright. We're proving it's symmetric. So we need to show that if x is congruent to y mod n, then y is congruent to x mod n. That's how you prove something symmetric.
Right.
So, assume that x and y are integers, where x is congruent to y mod n.
Okay.
Well, if x is congruent to y mod n, what's the definition of that? We say
N
x is
divides
congruent to y
x
mod
minus
n if n divides the difference. Perfect.
Okay, great.